Hello and welcome. Today I will talk a little bit about using donor spins in zinc oxide as qubits. First, a bit about their history. The oldest study I could find on donor spins in zinc oxide is this one from 1963, demonstrating electron spin resonance from defect ensembles at 77 Kelvin under ultraviolet irradiation. Another study in 1966 showed a resonance signal at room temperature by irradiating the sample with ultraviolet light for 60 minutes prior to taking the measurement and doing the measurement within a few minutes of stopping. They looked closer at the chemical identities of the donors that they were looking at. At some point, people stopped ultraviolet irradiating zinc oxide, and in 1971, a study in Germany observed the hyperfine interactions of donors, setting the stage for future interest. Later in the 2000s, people looked at the coherence times in different temperatures, reaching nanoseconds of pure phase coherence at cryogenic temperatures. With the great quantum spin search accelerating, people started to notice zinc oxide for its ease of fabrication and nice optical properties. But what are these qubits? Donor spins in zinc oxide function in many ways like a hydrogen atom with extra hardware attached that helps with physical confinement, initialization and readout, and of course decoherence. In a practical model of the donor level structure, the two lowest states are the up and down of the donor electron, but there are also two higher states corresponding to an exciton bound to the donor. The exciton consists of a spin singlet with spin 0 from an electron that joins the donor electron, and the hole that electron leaves behind. The hole has spin half, like the electron. In the presence of a magnetic field, this makes for 4 distinct energy levels. Interfacing with the zinc oxide entails using one of the exciton states as a lambda system. You can initialize the qubit in 1 by pumping the transition between 2 and 3, which is one of the exciton states. Zinc oxide excitons decay very quickly in about 1 nanosecond to either of the two lower states with roughly equal probability. So by selectively exciting the 2 to 3 transition, you will eventually end up with all 1. Readout is performed similarly, for example, by selectively exciting the 1 to 3 transition and waiting for a photon. If you get one, regardless of what color you get, the measurement result is 1. Since the selectivity of the excitation depends on strong splitting between the 1 and 2 states, there is a lower bound of about 2.25 Tesla of magnetic field for this pumping scheme to work, and it really should be even higher for practical purposes. However, there is a conflict, namely that large magnetic fields harm T1, and even worse, actually leave us unable to perform traditional microwave control of the spin qubit. Instead, zinc oxide donor spins are coherently controlled with a different scheme based on the detuning of the applied pulse from the qubit to the exciton transitions, giving us an equivalent degree of control. This is the rotating wave approximation Hamiltonian for this scheme. Intuition regarding how the qubit evolves under it in the limit of large detuning can come from adiabatically eliminating the large exciton states due to their relatively large energy under that assumption, yielding a much more familiar Hamiltonian acting only on the qubit system. Although for real calculations of fitting, it's of course necessary to describe evolution using a full master equation that accounts for decoherence. What makes zinc oxide donor qubits special? One thing that makes them particularly nice for computation is their optical properties. They have very high optical efficiency, a radiative lifetime of only about a nanosecond, and a low Huang-Rise factor, which measures the extent to which electronic transitions generate phonons. This means that the donor-photon interactions are predictable and reliable. Zinc oxide donors can be entangled with photons that they emit. If excited to an exciton state and allowed to radiatively relax without measurement of the emitted wavelength, the qubit state and photon color are now perfectly correlated. Another scheme involves separating two zinc oxide donors and placing a photon detector in between them. First, initialize both of the donors in state 0, then irradiate both of them simultaneously with only enough light to, at most likely, only excite one of them into the excited state 2. Then, wait for the detector to go off. if it only does so once, and it's impossible to tell which direction that the photon came from, and its color represents the 2-to-1 transition, then your two donors are perfectly correlated. In order to discuss the pros and cons of zinc oxide donor qubits, we should put them in the context of other solid-state qubits out there. One simple limitation is that it's usually used at cryogenic temperatures, which puts it far behind the likes of diamond and V's in terms of many applications like biosensing. However, zinc oxide's optical superiority puts it far ahead of diamond, which has notoriously weak optical properties in terms of time and fidelity of light-mediated operations like initialization and entanglement generation. Speaking of fidelity, one area where zinc oxide struggles is longitudinal coherence time. Diamond generally beats it by about a factor of 2, and donor spins in silicon beat it by up to 2 millionfold from their spin-free 2 Kelvin media. Zinc oxide donors also have an edge over 3-5 semiconductor quantum dots, which have a very spin-dense nuclear environment, while in zinc oxide, besides the donor, there's only the natural 4.1% abundance of spin 5 halves zinc 67. Here is a table that has some other important solid-state qubit types and some of their important metrics. The T1 spin relaxation time is limited by isotopic impurity and instantaneous diffusion. Isotopic impurity can be addressed with enrichment of material used to fabricate zinc oxide. Instantaneous diffusion, which also affects T2, refers to the coupling of donor spins to each other during the Hahn-Echo process. Echo cannot cancel out this coupling because the donor spins are rotating together, but this effect can be minimized using smaller pulses. Another challenge is engineering with zinc oxide donor spins. Donors in bulk zinc oxide have the best coherence, but they aren't necessarily the best for device integration. The best studies to date have gotten cryogenic bulk zinc oxide donor coherence up to Hahn-Echo dephasing time T2 of 50 microseconds and spin relaxation time T1 of 500 milliseconds. The Fu group recently took measurements of spins in zinc oxide nanowires and found their qubit potential to be not so shabby even compared to the bulk qubits. Using this, ongoing work is attempting to integrate zinc oxide donors into quantum memory and register by generating entanglement between a zinc oxide donor and a trapped ytterbium ion via photons, taking advantage of zinc oxide's superior optical interface. This interface role is likely where it would find its place among the many components of modern quantum technology. Thanks very much for watching. I hope you enjoyed.